Alright, my name is Professor Thomas, and today we're going to be looking at a very interesting topic of spectroscopy.
Ooh! Ah!
As you can see, my assistant here is very excited to be learning. The first topic we're going to talk about is absorbance. Now, absorbance is the property of an atom or molecule to absorb light. Taking an atom or molecule in the ground state and giving it just a little bit of energy to excite the electrons into the next energy orbital. The jumping of these electrons absorbs a light packet called a photon from the incoming stream of photons, and this difference can be detected and measured by a machine called a spectrophotometer. Now, my assistant here is going to show you a diagram where the first component is a light source, and that's usually a lamp that generates light. The next component is a piece of equipment that selectively lets through one wavelength of light. The next component is a slit and our sample in a cuvette. And then the last component is a reader that detects the amount of light going through and the difference in intensities from before and after, and displays it on the readout. Now, that's how a spectrophotometer works, but let's do a demonstration, because it's all good in theory until you can prove it. So, I have here a fancy-dancy flashlight. As you can see, the flashlight on the wall has a it's pretty intense. It's like blindingly white. Now, imagine we were to put something in front of that light that would take away some of the intensity, perhaps absorb some light. I have also a solution of copper sulfate. Now, copper salts are blue, and blue solutions can absorb light and keep it from emitting the other side. Now, when I put the blue vial in front of the white light, you can see the energy on the other side becomes blue. The light emitted from the vial becomes blue. This is absorbing the light and emitting it at a different light, and thus not letting all the initial light through. Now, that's about all I have time for in respect to absorbance, but the next spectrophotometer phenomenon that we're going to be looking at is called emission. Now, emission is much like absorption, but in reverse. When the atom gets enough energy, either from heat or high energy radiation, the electron jumps to the next orbital energy level for that atom. As the saying goes, what comes up must come down. And in this instance, it is absolutely no different. So, my assistant here is going to put a diagram in front of the screen. The circle with all the dots in it, that's your nucleus. And let's say this is a nucleus of lithium. Lithium has an electron in the n=1 orbital shell. And this electron is happy being where it is. Except when it gets light, let's say from heat, energy from heat, it gets excited, and it jumps all the way from n=1 all the way up to n=3. And when it's in or at orbital level 3, it has more energy than it did in n=1. And this makes it unstable. And so when the electron is unstable, it wants to return back to the ground state, and in doing so, releases light that we see as visible light. And in this case, as the electron drops from its n=3 to its n=1 state, it releases red light that I will show in a demonstration in but a moment. Now, let's show that demonstration because I can feel the excitement through the screen. So, here I have a petri dish. In this petri dish, I'm going to put a little bit of rubbing alcohol. This is 95% ethanol I got from the store. Now, when we put some salts in it, let's say lithium salts as before discussed, lithium salts burn a nice red color when their electrons get excited. So we're going to sprinkle a little bit of our lithium salt into our solution, and then I'm going to turn off the light, and we're going to light it up using our handy dandy lighter. You ready? 3, 2, 1. So, initially the alcohol burns blue, and if my assistant brings the camera a little bit closer, we can get an even better view of what's going on. So, the alcohol is burning off, and when it reaches enough energy, the lithium in the salts will start to burn a nice red color. I'm really hoping this demonstration works, and I don't think it is. Ah, there we go. So there are small red peaks. Demonstration enough. When the lithium gets hot enough, the electrons will gain energy, go up to their higher state, and release energy as they come down as red light. Now remember, cold glass and hot glass look the same. If you were to touch this, you would melt your fingers off. Be safe, kids. So, as you can see, lithium salts burn red because when their electrons go from their high energy state to their low energy state back to the ground, they release light, and in this case, red light. The last effect that we're going to demonstrate here is fluorescence. And fluorescence is when a compound absorbs light at a wavelength and re-emits that light at a lower or different wavelength and a lower energy. So, as my assistant again brings the diagram in front of the screen, as you can see, on the very bottom line, we have the ground state. And on this ground state, we have the electron being happy and where it wants to be. As soon as we shine some light on that electron, it jumps up to its to the very, very excited, most excited state, where it's not very happy at all, and it's just very unstable. And so in doing so, it cascades down ever so slowly, and it trickles down, and it releases energy that we don't see as UV or IR light. And then it reaches a semi-stable state where it is able to make the jump all the way from that, all the way back down to its ground state, and in doing so, releases light much like you're seeing on screen now with the highlighter. However, there is a better demonstration, and I will show you that in but a moment. So, in these three vials, I have three different substances. One of these vials contains a substance called tonic water, and tonic water is manufactured with a compound that's called quinine. And quinine is able to fluoresce under UV light, and I have myself a UV flashlight. I'm going to turn off the lights, and I'm going to shine my light, and you guys are going to see which vial contains the fluorescent compound. 3, 2, 1. So, one of these vials is not like the other. One of these vials, it's not this one, it's not this one. However, this vial, when put under UV light, glows. And that's because the quinine in solution is absorbing the energy, exciting its electrons, and releasing that energy at a wavelength that's visible to us. As in this case, well, you see white light, but I see blue light. And if you were to have a gin and tonic under UV light, your cup would glow. So, as a quick recap, absorbance is when light is going through a solution and the intensities change because light is getting blocked. Emission is when electrons get excited and drop back down to they go up to an excited state and drop back down to the same state, just in one fluid motion, releasing visible light that we see, and in lithium's case, red light. And fluorescence is when an electron gets excited to its most stable state, which is unstable, cascades through a semi-stable state, and then jumps all the way back down to a stable ground state, releasing light at a different wavelength that we see as visible light, as seen in the quinine solution, the copper sulfate solution, and the alcohol and lithium salts demonstration. Thank you for attending my lecture today. I hope you all enjoyed yourself. Make sure to stay safe out there, wear your mask in public, and study hard. That's enough from me today. I hope to see you guys in your next lecture. Have a good night.